So instead of an optimization problem, we'll start with the related rates problem, but we'll get around to the other fun word problems. So this is number 2 from absence practice exam 3. And the problem tells us that it's a related rates problem, which is kind of nice. But even if it didn't, we should be able to deduce that it's a related rates problem. What we know is that the length of each edge of a cubical pyrite crystal grows at 2 millimeters per year. We're asked to find the growth rate of the volume, and he even gave us the units. The volume in millimeters cubed per year. When the volume of the crystal is 27 cubic millimeters. Okay, why do I know it's a related rates problem? Because I've got rates that are something per unit time. Once I know it's a related rates problem, now I'm going into my 4 steps. That first step for related rates is just to identify what the rates are that we were given. Thank you. And what the rates are that we want to find. The rate that we were given is this 2 millimeters per year, and that corresponds to the length of each edge. It doesn't really matter what letter I use, but I'm going to go for L for length. So I'm going to say that DL dt is that 2 millimeters per year. And then the rate that we want, we're trying to find the growth rate in the volume. So I'm going to go ahead and call that dB dt for volume. And we already know the units are supposed to be cubic millimeters per year. Now, step 2 is to find an equation. Sometimes I need a picture for that. I'm going to go with I don't really need a picture for this. We know it's a cube. So I know that the volume of a cube should be the length cubed. Step 3, we're going to take a derivative. And with all of our related rates problems, we're taking that derivative with respect to time, unless something weird has been said in the problem. There are, for every single question in the textbook, for sure, we're taking that derivative with respect to time for related rates. Well, when I take the derivative here, I've got 3L squared times DL dt. Step 4 is to plug in the when. And in this case, our when was that the volume is 27. But we actually don't have anywhere to plug in volume directly into our equation. What we do need to figure out is the length. So if I take that volume of 27 and I plug it into our original equation, I'd have 27 is equal to L cubed, which means my length is 3. Then we plug all this stuff in. We were looking for dV dt. I know that my L was 3. And I know that our DL dt was 2. And we'll just slap our units on there. Cubic millimeters per year. And I suppose we could turn that into a nice number, right? 3 squared is 9, times 3 is 27. 27 times 2 sounds like 54. So I could say that's 54 millimeters cubed per year. Before I move on to new stuff, I do want to pause and see if any of the Babson folks have other questions from the practice midterm. Oh, can we go over all of the questions on the practice midterm? Was that what you were going to say? Let's start at problem 1 and let's see where we get. It's good practice. Everybody's got final exams. So anything we do is good practice in that sense. But let's take a look at question 1 from there, which is an implicit differentiation problem. Good times. So this time we're looking for the equation of the tangent line at 1, 4. And our curve is x squared plus the square root of xy equal to 3. Well, I know if we're going to take this derivative, it does not say y equals at the moment. So if we're going to do this derivative, it's going to happen implicitly. I will say that we have a choice because we have x and y being multiplied together underneath that square root. One choice that we have is to think about that as the square root of x times the square root of y. Or we can think about that as x times y all to the 1/2 power. I think it's going to be easier if we think about it as square root of x times square root of y. But I don't know that that's what you would think to do on a test. So I don't really know. But I'm going to do it that way. And before I take the derivative, I'm going to rewrite this. Either way, it's going to be a little bit messy. But I'm going to write that as x to the 1/2 times y to the 1/2. Now I know that either way it's going to be a little bit messy because I've got a product rule, but by splitting it up like this, I don't have to do so much chain rule and then product rule. I can kind of just have the product rule piece. Now I'm ready to take a derivative. Anytime we're finding the equation, I lied, I'm not ready to take the derivative because I'm looking for a tangent line. And if it were me, and I might possibly be worried about running out of time, I'm going to go scoop up my partial credit first. And I'm going to write y minus 4 equals m times x minus 1. And I'm going to get that by finding dy dx at 1, 4. Honestly, that's going to get you partial credit. Maybe not a lot of partial credit, but it really will get you partial credit. So I'm going to take that first in case I run out of time somewhere else. Now I'm ready to take the derivative. Well, when I take the derivative of x squared, I'm going to get 2x. Here, I've got a product rule. So the derivative of x to the 1/2 would be 1/2 x to the negative 1/2. Then I'll leave the y to the 1/2 alone, plus I leave the x to the 1/2 alone and multiply by the derivative of y to the 1/2. And on this piece, because we're taking the derivative of something with a y in it, we're going to remember, yep, better tack that on. And on the right-hand side, don't forget, this is like one place that I do see a lot of mistakes. When you take the derivative of a number, it goes to 0. We have a choice to make right now. I actually only care about this value for dy dx at one very specific point. So we either can do the algebra over here to get the dy dx by itself, or we can just plug the number in right now and kind of do the arithmetic on it instead of the algebra with it. Either way works. I'm going to go with let's plug the number in. So this says I'm going to plug in x equals 1 and y equals 4. And if I plug that in, 2x will just be 2. The square root of 1 is 1, and 1 over 1 is 1. So that'll be 1/2. Y to the 1/2 means take the square root of 4, that's a 2. X to the 1/2, that's 1 again. I've got 1/2. Y to the negative 1/2, I would take the square root of 4, but then that negative means I'm going to do 1 over that. Question? This 1/2 and from that 1/2. This 1/2 is from y to the negative 1/2. Was that your question? Okay. Times dy dx. Well, 1/2 times 2 is 1. 2 plus 1 is 3. So over here, I could have a -3. And 1 times 1/2 says I've got 1/4 dy dx. So I would get that dy dx was equal to -12. Which means I can put that into my equation for the tangent line and say y minus 4 is equal to -12 times x minus 1 and call it a day. Pausing in case there are questions about that one. Yeah. Like where I got the 1 over 4 from? So, oh, from here to here. From here to here, you could either think about that as dividing by 1/4 on both sides. I choose to think about that as multiplying by 4 on both sides. Because if I multiply by 4 on both sides, then they cancel out over here. And I get that, and I'm left with -12 on the right. Yeah. So I've got 1/2 times 2. So that would be a 1. But then I've got 2 plus 1. So together that's 3. And I subtracted 3 from both sides because this piece didn't have a dy dx in it. Question.
So you want to give it an x value? Is there a way you can like quantify it so you can plug it in?
Yeah, that's a good. Yeah, so if as long as you've been given an x value, you can plug it into the original one and find y. Now, if you're not given an x value, you have to do the algebra. Yeah, but as long as you're given an x value, personally, I find this easier to just plug it in first because you're gonna have to plug it in eventually anyway. But this way, like you kind of trade algebra for just maybe messy numbers, but at least it's not messy algebra. Yeah. So the next 2 questions on this midterm are like more practice with increasing, decreasing, concave up, concave down, inflection points, all that good stuff. So Sure. Why not? We can do these. I'm going to take the derivatives pretty quickly though, because I think that when we're talking about determining the increasing, decreasing, concave up, concave down stuff, usually the sticky point is the using either a sign chart or a number line to like figure out what's going on. Usually on these problems, the derivatives are not the messy part. So if I look at 3, the function we've been given is actually pretty similar to one we've worked with previously. So I've got x over x squared plus 1. And on this one, we were just trying to find the intervals for increasing, decreasing. So I'm going to fast forward my derivative a little bit here. I know that I'm going to need a quotient rule, but I'm going to talk through it quick. Derivative of the top is 1, leave the bottom alone, minus, leave the top alone. Derivative of the bottom is 2x. Then we need to take the entire denominator and square it. Well, on top, when we multiply everything out, that's going to look like x squared plus 1 minus 2x squared. Which means x squared minus a 2x squared, that leaves me with a 1 minus x squared. And I would choose to factor that as 1 minus x times 1 plus x. So if I went to find, I'm just going to write this as f prime. So if I went to get my number line going here, I'm looking for anything that makes the derivative equal to 0. So in this case, 1 and -1, and anything that makes it undefined. But that denominator can't be 0. Because x squared plus 1 does not have a root. So we would just be looking to plug numbers in and figure out where it's increasing and decreasing. Also, the bottom is always positive. So I don't even have to worry about plugging the number into the denominator. It won't affect the sign. So when I choose our test points here, I'm going to go with 0, 2, and -2. I really only have to plug it into the numerator. And you could choose which looks easier to plug it into, 1 minus x squared or the factored form. If I plug in 0, I'm going for the not factored form because 1 minus 0 is positive. We're increasing. If I plug in 2, I'm also going for the not factored form. 1 minus 4 is negative. And when I take that x equals -2, stick it in here, -2 squared becomes a +4. 1 minus 4 is negative again. And there we are. I don't think this question asked us to. But -1 would be a relative minimum and 1 would be a relative maximum. The one thing that's a little bit tricky in how this is phrased is we are asked only to consider from -3 to +3. What that means is that when we write our intervals, we're going to stop at -3 and +3. So when I say that it's increasing, I would say that it's increasing from -1 to 1. But I would say that it's decreasing from -3 to -1 and from 1 to 3. I'm going to change my mind on that and make these 3s brackets. By the way, I'm making the 3s brackets because at 3, this is still increasing. F prime is decreasing. F prime is a negative number. Normally we do open intervals when we're talking about increasing and decreasing, because the places that we're like stopping at on our number line are places where the derivative is 0 or undefined, not places where it actually has a positive slope or a negative slope. What's different in this case is we really do have a negative slope at both of those endpoints. So it is still decreasing on that interval. Cool. Good times. And since we're on a roll, and this next derivative will be super quick to take care of. Number 4, our function was x to the 4th minus 6x squared. And we're looking for where it's concave up and concave down. So I know that I'm going to need 2 derivatives. And that first derivative, I'm looking at 4x cubed minus 12x. And for my second derivative, I'm looking at 12x squared minus 12. So if I'm trying to figure out where it's concave up and concave down, I really need this to be equal to 0. And then I'm going to get it factored. And it looks to me like that's going to factor as 12 times x minus 1, x plus 1. So I really have the same numbers on my number line as last time. I like to remind myself what my number line is of, so I remember where to plug it in. So I'm looking at my second derivative because we're talking about concavity. And I know that if I choose test points of 0, 2, and -2, I'm just going to be really careful. Our domain is not restricted at all, so that's what we're going to do. Again, you have a choice of wherever it looks easier for you to plug the numbers in. Would you rather plug it into the factored version or the not factored version? For 0, I'm going not factored all day long. That's definitely negative, which means we're concave down. If I plug in 2, if I throw that in our not factored version, that looks positive to me. We're concave up. When I plug in -2, once I square it, it's positive again. So 12 times +4 minus 12, positive. So I know that I have points of inflection when x equals -1 and when x equals +1. And if I were doing the concave up, concave down bit here, looks to me like we're concave up on -1 to 1. Again, my concavity is 0 at -1 and at +1. So we're not going to include those. That's why we have the rounded brackets or parentheses. And we're concave down -infinity to -1. And, oh no, I got that backwards, but I can fix it because I have an eraser. We were concave down on that middle section and concave up on the edges. For the inflection points, it's a point. A point should always be an ordered pair with an x value and a y value. So I know -1 comma something and +1 comma something are going to be my 2 inflection points. But I need to plug that into the original function to get a y value back. When I plug in 1, that would be 1 minus 6, so -2. When I plug in -1, that is also 1 minus 6 or -2. Now there's an extra question here that's great because we're going to use this when we start talking optimization in a second. The question says, the function has a local extremum at x equals 0. Is it a local minimum or a local maximum? Now, the intent of asking this after having you do the second derivative is not that you will go back and do something with the first derivative. The intent of asking it at this point is for you to say, hey, look, we were concave down at x equals 0. I can't be concave down and be at a local minimum. There literally isn't a way to be standing at the bottom of a valley, but somehow be concave down. So I know that this is a local maximum because f double prime at 0 is less than 0. And if we're concave down, that means we were standing at the top of the hill, not the bottom of the hill. And we did the last problem last time, so I'm skipping it for now, but in case you were not with us on Tuesday, I'll do the fast forward version. P was negative x squared plus 60x minus 20. We're supposed to use differentials to estimate the value of dp. Well, those differentials mean that I'm taking the derivative, which hopefully we're pretty good at by now. And then that differential piece is that I'm really thinking about this by multiplying both sides by dx. So that dp is equal to negative 2x plus 60 times dx. And then we've been given some numbers. So we were given that x is 10. And we were given that dx is 0.5. And that's 40 times a half. So we got 20. Cool. We made it through Babson's whole thing. Good times. Pausing for a second in case there are questions on that. And then get ready for some more fun with word problems. Oh yeah. Question. Like how I got the numbers or how I know they're inflection points? Mm-hmm. Oh, so the negative 1 and 1 are coming from the places where my second derivative was equal to 0. Once I know where my second derivative is equal to 0, then I know that's potentially an inflection point. I have to check on either side of that. Did the concavity actually change? So like negative 1 changes from a concavity that's positive to a concavity that's negative. Positive 1 changed from a concavity that was negative to a concavity that was positive. So that's why I know those are the x values where we should have an inflection point. To get the y values, I plug them back into the original function. Yes. I don't know. I think they would be -5. I don't, yeah, cool. Did I like write a 2 when I meant to write a 5? Maybe. Good deal. So if I do f of 1, that's 1 to the 4th minus 6 times 1 squared. That sure looks like a 5 to me, whether it was a positive 1 or a negative 1. Good call. Sorry. Well, when I put the negatives in here, oh, the overall thing is negative, yes. Did I make any other mistakes? Let's make sure we got it right before I flip the page. Okay, so there are a couple of requests to do another one, kind of like problem 5. So, cost of producing a rolling chair. Yep, I'm really not inspired. There are rolling chairs in front of me. That's all I got. Cost of producing a rolling chair is given by C of X equals, I'm just making this up. I have no idea how much it costs to produce a rolling chair. Just want to be clear on that. Let's go with 100 plus nope, I want that to be 100 times, yeah, okay, 100 times 1 minus, oh, this is really, yeah, this is like I've just really completely made up some garbage. But it'll get the point across. Where X is the number of chairs produced. Estimate the change in cost if production increases from X equals 10 to X equals 11. Okay, there's kind of a lot of words and things on the page. So we're gonna dissect things a little bit, but I am gonna say that based on the practice exam that was written, I think it's possible that Babson would explicitly tell you to estimate the change in cost and then tell you that he means DC if the production increases from X equals 10 to X equals 11. And I think he might tell you that that means DX is equal to positive 1. So for the question on the chat, yes, if we go from 50 units to 51 units, that means that the DX is 1. The other thing that we need to know in the problem is that in general, when we're using a differential to estimate something, there's like a nice value that we want to plug in and some messier value that we're trying to find information about. If I'm looking at 10 or 11, 10 is the nicer number to plug in. We're definitely plugging in the 10. So in terms of the differential piece of it, we're just going to take that derivative of dc dx. And since that's hiding up there, let me just write C down here so that they're kind of next to each other before I get started. So C was equal to 100 times 1 minus x squared over 4 plus 500x. I'm going to give everybody a minute to take that derivative. You are totally welcome to rewrite that before you take a derivative. I'll leave that up to you to decide. I chose to distribute the 100 in. Doesn't mean you had to. Just figured it looked nicer that way. 100 divided by 4 is 25. Yes, reality check, making sure I'm got my arithmetic going well. Okay, so when I take the derivative, I think I'm going to get negative 50x plus 500. Oh, that's really unfortunate. So like I just made the problem up. I didn't mean for it to be 0, but okay. I accidentally made up a thing and it's going to work out to be 0, whatever. So to estimate that change in C, or to get that DC by itself, I'm going to multiply both sides by dx. And then really, we're estimating this when x equals 10 and dx equals 1. Again, the reason I'm using 10 is because in general, on these estimation problems, we're plugging in the nicer number, not the messier one. So I'm going to have negative 50 times 10 plus 500 times 1. And this is where, because I totally made up the problem, this ended up working out to be 0. Which, by the way, since we have just minimized our marginal cost, it's probably an opportunity to maximize profit. Accidentally. Okay. Dun, dun, dun. It's about 11:10. Here's my plan. At 11:15, I'm going to start doing optimization stuff. For the Babson folks, if you're like, I cannot cram one more thing into my head right now before the test, maybe go do something else and study something that's going to be productive for you for the test, right? I promise we'll do more practice with optimization stuff next week on Tuesday. We don't have class next Thursday. You don't have any of your classes next Thursday, but we'll do more optimization stuff next Tuesday as well. So you're also welcome to stick around and do some optimization stuff. There will be practice with derivatives and practice with number lines happening. So, and some word problems. So anyway, take a little break at 11:15, optimization.
Is there something like I should go?
Are we ready for some optimization? Woo! For good and bad, this right here is actually maybe most of the entire reason that for your major, whatever it is, you were required to take calculus. So the real world is always all about optimization. I'm looking to make it cheaper, faster, smaller, bigger, lighter. But most of the time, optimization is really what we're trying to do out there. Saving money and saving time being the two biggest things. Optimization problems at their heart are just saying we are trying to find those relative maxes and mins. Or given some sort of constraint, we're trying to find an absolute max or a min. We already know how to do that. We just need an equation to take the derivative of it. What makes optimization really fun is usually we're not given an equation. Usually we're given some sort of context and we have to build an equation out of that context. So I'm going to use the props I have available to me in the room. It's the box. And somebody had to design this box. And whoever designed this box, trying to see if it's got some recycled paper content, not that I can tell, but someone had to design this box. And if they were trying to make this box as cheaply as possible, what do you suppose they were trying to optimize? Oh, I should say there's another issue here. Someone decided that the box needed to hold 50 masks. So there was some amount of volume that we had to be able to contain. We needed to fit 50 masks in it. But there were other shapes of boxes they could have chosen. And I bet someone worked an optimization problem that ended up with exactly this shaped box. So I'm going to fake some stuff. Let's say that I needed to build this box. Oh, and I know I kind of asked a question. I didn't mean for it to be rhetorical, but then no one answered it. So sorry, since it's here and it's empty, I'm taking it apart. So give me a second. This is what someone optimized. Someone figured out how little cardboard could be used to construct that box. Now this is an optimization. Check it out. We cut corners out of it. There are like all of these notches. I guarantee someone figured out, now really they probably did it by trial and error. They probably did not write a calculus problem. Who am I kidding? But somebody figured out that they could make this thing lighter. They could use less material. It didn't have all these things in it. Okay, back to something that we can tackle as a calculus problem. Let's just say that my thought was, we're going to try to build this box. I need this rectangular box. I'm going to need it to hold I'm going to need it to hold 54 cubic inches is what I meant to write, but we'll just turn that into a C. I need it to hold 54 cubic inches. Now, there are I need this rectangular box to hold 54 cubic inches. I'd like to find the box with the smallest surface area. Now I'm going to add one other constraint in here, and we all know that this box did not magically arrive in this room. It probably, based on the fact that it was constructed in France, it probably got here on a boat and then on a truck. So the reality is there's probably some other constraint on this box, not just volume. So I'm going to say that for packing into the shipping container, it needed to have a square end. So I'm going to say the box with the smallest surface area and a square end. Oh, and what does it mean to find? This is a little bit vague. Find the box. I don't know. Maybe that's the vagueness that your instructor would use. But we're going to find the dimensions of the box. How about that? Of the box with the smallest surface area and a square end. So I said that most of the time with these optimization problems, the hard part is coming up with the equation. We know how to take a derivative, set it equal to 0, do our number line thing, all that good stuff. So to find the equation, I am always going to hone in on what is the word that ends in EST. Now, it doesn't literally always end in EST, but what's the thing we're trying to optimize? In this case, the thing we're trying to optimize is the surface area. So I'm going to start by writing an equation for surface area. And I'm going to go ahead and draw our box. I don't draw super well in 3D, but I do take boxes apart really well in real life. I hate cardboard. No, I don't hate cardboard. It's just, I wish we didn't have so much cardboard from shipping stuff. So I said that it needed to have a square end. So if I called this side X, this side would also need to be X in order that to be a square end. But this length could be something different from X. And in fact, it is on our real life box. So I'm going to call that Y, which means that when I go to find the surface area of this thing, the surface area is me adding the areas of all the sides. Well, this front side of the box is a rectangle that's Y by X. But that's the same as the back side of the box that we can't see is also Y by X. And the top of this box is also Y by X. And you know what? So is the bottom. So all told, I've got 4 of those. And then we've got those 2 end pieces that have an area of X squared. Now I've got this formula, right? I've got my surface area is equal to 4xy plus 2x squared. And I look at that and I'm like, yes, I have an equation. I know how to take a derivative and set it equal to 0. Oh, darn. We have 2 variables. I sure hope we know something else. And that's the key to every optimization problem. There is something else we know. That something else is usually a constant. And in this case, the only other number we've got in here is 54. Well, if it needs to hold 54 cubic inches, don't put the cube on that because it was weird to say inches, 54 cubic inches, then that's volume. And the volume of this thing is Y times X, or Y times X squared. So I need this to hold 54 cubic inches. And if it's going to hold 54 cubic inches, then this becomes, sometimes we call it the constraint. I've heard people refer to it as our helper equation because it's going to help us to get rid of the y over here. It doesn't actually matter which letter I solve for, but if I tried to solve for x, I'd end up with a square root. And none of us wants to take a derivative with the square root if we can avoid it. So I would choose to make this say y is equal to 54 divided by x squared and plug that in over here. That's going to turn my area equation into 4x times 54 over x squared plus 2x squared. And per usual, I'm going to choose to clean it up before I take a derivative if I can. So one of those x's will cancel out. 4 times 54, let's see, 4 times 50 would be 200, 4 times 4 is 16, so 216 x to the negative 1 plus 2x squared. Now we've gotten finally to the really calculus-y part. So go ahead and on your own, take a derivative, set it equal to 0, get your number line going. Let's see if we can find those relative maxes and mins. Hopefully the relative minimum, since we were looking for the smallest surface area. Hopefully we wrote a problem that has a relative minimum. Fingers crossed. Did we find any critical points? Are they gross? I have no idea. Well, if it factors great, I think you're going to need a common denominator because you got fractions. Yeah. But at least, oh, it worked out. Negative doesn't sound good. I think you're okay. I don't think you have a negative. I mean, there's like a negative in there, but I think once you move it, it's gonna work. Just so we can do the algebra together, your choices are to like factor out an x to the negative 2, which I think is a little bit weird, but totally works. Or to think about these as fractions and get a common denominator. I don't actually care which version we play. What do we think? Did any of you find a common denominator or did you factor? Okay, let's go common denominator then. So I'm going to write that as negative 216 over x squared plus 4x squared over x squared. If I multiply the top and the bottom, nope, x cubed, 4x cubed. Does that sound better? 4x cubed, multiplying the top and the bottom of the 4x piece by x squared. So on top, I'm just, well, it doesn't matter. If I put all of that together, I've got negative 216 plus 4x cubed all over x squared. Now, if I set that equal to 0, a couple things to note. X equals 0 would make this undefined. But also we had an actual box. If x were 0, we have problems. We don't actually have a box. So x equals 0 is kind of like that boundary point. I can't actually go to x equals 0. So if I focus on the numerator here, negative 216 plus 4x cubed is equal to 0. I would just move the 216 over. So x cubed would be 54. Which would make x the cube root of 54, which we could simplify a little bit if we wanted to, but I wouldn't worry about it. This is where, when we're doing these optimization problems, right? Then when we were doing this as an increasing, decreasing relative max min thing, we would find that and then like get a number line or a sign chart and have these test points. The nice thing about doing optimization problems is because of our real world context, we can think about this actually as an absolute maximum or minimum problem. When we have absolute max or min problems, all we have to do is check the endpoints and check our critical point. Additionally, we can think about, and this is my favorite way to decide that that's a minimum, is to just take the second derivative and plug that in to see if we get a positive number or a negative number. So those are 3 options for how to decide whether it is really a max or a min. So if I go by the second derivative test, if it's going to be a relative minimum, I'm hoping that my second derivative works out to be a positive value. So I'm going to find a double prime. If I bring that -2 down, 2 times 216, that would be 432. My negatives will cancel out, and I've got x to the -3rd plus a 4. And remember, I don't care what the number is. I just have to figure out if it's positive or negative. Sure looks like it's going to be positive to me. So that second derivative evaluated at the cube root of 54, whatever it is bigger than 0, which is good. That means that we're concave up, which means this represented a minimum. And then kind of similar to what we had to do with related rates problems, I do want to be careful about units and sort of how I'm reporting out that final answer. And if we had to find the dimensions of the box, that means I've got to give an x value and a y value. So I would say that x is equal to the cube root of 54 inches. And y, I'm not going to bother simplifying it, but if I want to know what y equals, I'm going to look for an equation that I already solved to say y equals. And plug it in. So 54 divided by the cube root of 54, whole thing squared, inches. Now I'm actually really curious. Obviously, I faked the dimensions of the box anyway, but what is the cube root of 54? 4, 2, 1/3 power. Okay, so the cube root of 54 is like 3.78-ish. And that is about to get ugly. That thing squared. Nope. Okay, I was trying to do this quickly. Clearly a real calculator would be helpful, but since I don't have one, 54 divided by, I got this. 3.78 squared. Oh, that's interesting. Okay, so if we had just gone on, clearly the manufacturers of this box did more than just surface area. We did not end up with the magic dimensions of this box. But it's okay. So it was a good thought. Shall we do another optimization problem for more practice? Okay. I won't take apart any more boxes this time. For this one, how much time do we, okay, this is like a really classic problem. No, this, we'll go with this. This is a classic problem, but something that's a little faster to figure out. We want to find a positive number for which the sum of its reciprocal and 4 times its square is as large as possible. Some of the optimization problems in the book are really just kind of like this. They're not even pretending to be real world-ish. We're just doing some stuff with numbers. How do I know it's an optimization problem? Because I've been asked to make something as large as possible. Where do I start for finding an equation? I need an equation for this thing that it's telling me to make as large as possible. So I'm just going to start writing the pieces. The sum, so I know I'm going to have addition of its reciprocal. Well, I guess I need something to call the number. I'm going to call the number n because it's a number. So the reciprocal of that number is 1 over n. And 4 times its square. So 1 over n added to 4n squared. And that's the thing we're trying to make as large as possible. So I don't really know what to call it. I'm just going to call it f because that is now my function. This is accidentally fairly similar in form to the one that we just did. but without the context. So I have this equation, but it's already in terms of one variable. Sweet. We can just take a derivative and set it equal to 0. How are we doing? We got a derivative. So I'm going to say my derivative looks like negative n to the negative 2 plus 8n. And I'm going to do the same thing we did last time and get a common denominator. So that's negative 1 over n squared plus 8n. But I'm going to make that 8n cubed over n squared. So I've got 8n cubed minus 1 all over n squared. Same kind of thing as last time. We know that we need this number to be positive. 0 is technically not positive. Also, 0 would make this thing undefined, so that would be bad. But if I set that equal to 0, I think on top, I'm just going to get 1/2. I don't know how picky your instructor or realistically the TA grading things is going to be, but I would say we should still show that this is as large as possible, meaning I would want to show that my second derivative worked out to be negative if this is going to be a maximum. So when I take that second derivative, negative 2 times negative 1 will make that a 2n to the negative 3 plus 8. And if we plug in the n equals 1/2, then my second derivative at 1/2 would look like 2 divided by 1/2 cubed plus 8. I'm getting nervous. That looks positive to me. Maybe someone wrote a bad problem. I stole this problem from a random worksheet that was laying in the classroom again. Looks to me like that's a positive number, whatever it is. And if my second derivative is positive, that would imply that this thing was concave up, which would mean that we actually just found a minimum. Let's resolve this. If I graphed this thing, like if I just thought about f of n for a second as being 1 over n plus 4n squared, if I don't put an upper bound on this, this can be as large as possible, right? Like if I don't, this part's going to go to 0. But this part goes to infinity. So this is a poorly written problem that I found randomly in the classroom. 2 ways to fix it, we could say is as small as possible. The other option for fixing it would be to say there is no such number. Cool. Good times. That's what I get for using random
So
problems from the classroom.
most of the time though, we get a problem, it's in the secondary. It's like what we wanted to show.
Yes. The only time that I've seen it not work out that way is if you were given an additional constraint. So like on this problem, if this had said, find a positive number less than or equal to 10, and all of that same information, then getting the answer that we just got would mean that we would have to say, oh, well, the number that we should use is 10, not the thing that we just found, because the thing that we just found was actually a minimum, not a maximum. So there are some problems that are going to work out like this, where we're going to have to know that the final answer would be that n is equal to 10. But other than that, all the rest of them, it usually works out that whatever point you found as a critical point is the correct thing you were looking for. It's a max if you were looking for a max, or a min if you were looking for a minimum. Yeah. I think we should call it a day. I've got office hours starting in half an hour over in El Centro. I have Zoom office hours tomorrow from 2 to 3. And if I don't see you again, have a lovely weekend. See y'all on Tuesday. You're welcome.